Okay,
Yes.
so now, just as a quick review for if you're checking back to see this online, okay, counterclockwise rotation is positive, clockwise rotation is negative. Okay, we have theta is our angular displacement, it's in radians. Radians is a ratio of arc length to radius. Arc length we use the letter S to represent it. Radius is in R. And then, as an example, for a full circle, theta in radians is equal to 2 pi r over r, which is equal to 2 pi radians. By the way, units of radians. Okay, you think of, okay, we said it's S over R. So this is measured, so theta in radians, okay, you always think of the unit being the radian, but a radian is just a ratio of distances, meters over meters. So technically speaking, okay, you can use radians in your, as you're describing whatever variable you're talking about, but it doesn't alter anything as far as meters per second squared, or if you're doing kilograms or whatever. It doesn't alter the actual unit measurement. Yes?
Since like going clockwise, you have negative, like a negative measure. Is the arc length, if you're moving clockwise, negative?
The displacement would be negative.
Okay.
So yeah, you can definitely have a negative displacement going clockwise. Okay. And so the displacement, well, angular displacement typically would actually be a delta.
Are we working with displacement per second?
Well, it'd be
Changing
great.
arc length per second.
Yes, that would be angular velocity, which is the next thing.
Omega.
Okay. Delta theta, I really should call it a delta theta. Theta would be your angular location, I guess. And then we have the actual displacement would be a difference between those two things. Okay. Now, we have, along with that, when we talk about change in location, okay, or change in position with respect to time, what did we call that? Velocity. Okay. Now we have same thing with angular velocity. Okay, we have angular velocity omega is equal to change in theta, so the displacement per unit time. Okay, and so when we're looking at omega for the units of omega, this is equal to radians per second.
So wouldn't that just be like per second?
So technically speaking, that would be per second. So when you do something like V equals omega R, okay, the reason why those units work out is because V is in meters per second equals omega, which is per seconds, times R, which is meters, and so this work out. Now, relationship here between, okay, we have theta here is equal to S over R. So we can rearrange this. The arc length is equal to the angle times the radius. Okay. Well, let's just say I do this with respect to time. The change in arc length with respect to time is equal to the change in theta times R with respect to time. Now, we assume R to be a constant. It's not always a very good supposition, but for our purposes, it will be. Okay? So R we can pull out. So what I'm left with here, what's delta S over delta T? What do we, that's a change in location with respect to time. What do we call that?
Velocity.
Velocity. Okay, R doesn't change, so I pull R out, and we're left with delta theta over delta T. What is delta theta over delta T? Angular velocity, omega. Okay, so we have V equals omega R. So this is, so our relationship between arc length and angular position is S is equal to theta times R for velocity, it's v equals r omega. So,
Does air resistance inhibit?
Derive it.
okay,
Sure.
Especially if it's got a, air resistance is affecting one side more than the other, because then you have to create a torque. So that's where air resistance would definitely play a because if you have just a solid wind field, if something is spinning, okay, in this direction, okay, and I put wind blowing in this direction, okay, here it's going to give it a push and help it. Here it's going to try to, because it's going this way, it's trying to stop it. Okay, so the net result is nothing. But if I put it all off to one side, I concentrate on one side, that's going to help give it a push. Okay. Now,
So like when you push a wheel down on one side, you hit
Create a
it.
tornado.
all right. So now, along with that, we have angular velocity. We have angular position, as theta and omega. But if we have a change in omega with respect to time, okay? So this is angular velocity. If we have a change in angular velocity with respect to time, okay, what do you think that's going to be called?
Angular acceleration.
Angular acceleration, okay, which we call alpha. So this is angular,
Do we call it fish?
can't call fish.
This is where conditions.
Okay? So delta theta, so this change in angular acceleration, angular velocity with respect to time is called angular acceleration. We use the Greek letter alpha for that. Again, units for alpha will equal, this is going to be radians per second over second, so this is radians per second squared. Again, when we combine this with other variables, the radian is a unitless measure. Okay? So alpha is our angular velocity, angular acceleration. Sorry. Now, a couple things with this. Well, I can relate the angular. So let's just say that we have something spinning here, and it's going around, let's say in this direction. It's got some radius r. Okay. We can look at a spot right here. We'll call it point P. At point P, as this spins around, we can look at the velocity of that point P. We can look at the angular velocity of that point P. We can look at if that angular velocity is changing. Okay, we can look at the angular acceleration. We can even look at the actual tangential acceleration. Okay. Now, it will definitely have a centripetal acceleration here. Okay, I was going to ask. The direction is going to be inward. It definitely has a centripetal acceleration inward. That's v squared over r, or omega squared r. But it also has, if the actual rate of rotation is changing, okay, we also have what's called a tangential acceleration. Okay, centripetal acceleration, okay, that points in. Okay, a tangential acceleration, so that's AC. I'll call this AT. Okay, tangential acceleration is in the direction of motion. In other words, it's changing the rate at which it's spinning.
So the way the velocity is actually going, tangent to the pedal is speeding up.
That's why they call it tangential. Okay, so now your tangential acceleration. Your tangential acceleration is equal to, well, let's do it like this, where we have v is equal to omega r, okay? So if I take, and I'll do a calculus style instead of just delta, dv dt
Go back to 50.
is equal to, assuming r is constant again, d omega dt, and using calculus formulation this time. Okay, what is dv dt?
Acceleration.
Acceleration is equal to r times, what's d omega dt?
Angular acceleration.
Alpha.
Angular acceleration, alpha.
So wait, the acceleration of what?
And this is the tangential
Okay.
acceleration. Okay? And a very good question would be, well, if something is spinning around and it's increasing its speed, would its actual acceleration therefore be, how would I calculate the actual total acceleration? Well, if I have an acceleration that points like this, tangential, basing it off this, and like this, centripetal, how would I calculate the actual total acceleration?
Okay.
Pythagorean theorem. Okay? We don't really get into that very much here. Either in, if you take a higher level physics class in college, you'll probably see that. You'll probably take a either a calc, your depending on how your college sets up calculus. I know when I went to school, we took a class called vector geometry, which was kind of a it was a pull-out course from what calculus was. We covered this in a separate course from calculus, or you'll take this in your calculus course in college, and you'll go over that. Tristan.
Is that v in the v equals rw, is that tangential velocity?
That would be a tangential velocity, yeah.
So,
There's no centripetal velocity per se.
yeah,
So your velocity in total comes from here.
okay.
Okay.
Wasn't omega angular velocity though?
Yes, this is omega is angular velocity.
So, what would v be then?
V is your actual, like your meters per second, how fast you're going.
Okay.
So, like I was saying, if you're right here, I can say how fast am I going? That would be V.
Yeah.
How fast am I spinning? The rate at which I'm spinning, that would be omega.
So angular velocity is how quickly you're spinning, and
Yeah.
velocity is how quickly you're spinning.
Yeah, it's your actual speed.
So wouldn't that just be speed and not velocity, or?
Well, yeah, you'd have, if you want to make the velocity, like if you're right here, you'd say it'd be your speed
Yeah.
dash, or make it a vector. Okay. All right, so now we have that. So just something to think about as we get into the, as we move through all this.
Why?
The,
Why do you have my signature?
okay, we have X,
You can use my signature.
which goes with theta. We have V, which goes with omega. We have acceleration, which goes with alpha. Time is time. That doesn't change, okay? That doesn't cost it.
What are you, Tristan?
You're on film.
Now it was underneath it.
Yay.
Rewind.
Okay. Okay.
So,
Now it's off camera.
would rotations per minute be similar to omega? Or would that be
That would be similar. That would be a measure of omega. But you have to be careful with the you have to be careful with the units, guys.
It's, yeah, no, it's not radians, it's
Yeah.
full rotation.
Yeah.
What was that?
Now, one final thing before we stop. Okay. The question is whether or not these values are vectors. Okay. Here's the thing: angular velocity, angular acceleration are vectors. We don't really have to use them as vectors though, because we can think of it as we can give our direction as plus and minus. In more complicated situations, you would definitely use them as vectors, especially when we start talking about angular momentum. However, angular position, okay, angular displacement is not a vector. Okay? Here's the problem. Okay? If I take this book, okay, you can treat it with a positive and a negative like you would anything else. But here's the problem. When you add different displacements together, you don't get the same thing. Okay? And that has to happen in order for it to be a vector. So angular displacement is not a vector. If I take this book, okay, now I'm going to rotate it 90 degrees this way, and then 90 degrees that way. And it looks like this. Okay? So what did I do? I rotated it this way, okay, and then down. So now if I rotate it down, if I do the same thing but in the opposite order, down and this way, you don't get the same thing. Okay?
Wait, do that again.
So if I do it like this, okay, if I rotate this way and then down, if I do it that order, I get it like this. If I rotate it down first and then this way, you get this.
This is blowing my mind.
Because you don't get the same
How does that
result,
happen?
because you change the order, it's not a vector.
This is what
A vector, no matter how you add it, like A plus B has to equal B plus A. Well, this is, if I do an A plus a B here, I get one thing. If I do an A plus a B, let's see, what is it?
What's that?
If I do A plus B, I get this. If I do B plus A, I get this. So you don't get the same thing. All right, so that's going to be our time for that.
That just blew my mind.
Seriously. How does that work?
Take some books, it's like everything
Ow.
you think is
Why
wrong.
would you throw that?
It's a soft sandwich. I doubt it hurt that bad.